This is an example of a topping cycle CHP or combined heat and power system in which there is a turbine with a steam flow rate into the turbine of 10,000 kilograms per hour. The back pressure steam turbine drives a 95% efficient electric generator. Then how many kilowatts will be produced in that electric generator? The turbine has so hang on, the steam is going to have an enthalpy of 2,800 kilojoules per kilogram going in, and then it has used up 200 kilojoules per kilogram by going through that turbine and making that work. Important to note here is that we're assuming that is an insulated turbine, okay? So that this is our engineering assumption that there's no heat loss as we went across that turbine. So this enthalpy change from 2,800 kilojoules per kilogram to 2,600 kilojoules per kilogram is not, all goes into work basically. So what is the work energy that would be produced? So the work produced would be measured in, well, I'm asking right here for kilowatts. This work energy would be produced, measured in kilowatts of energy, would be that mass flow rate into and out of this turbine times the change in enthalpy. The change in enthalpy as we went across that turbine, assuming none of it was lost to heat. So how many kilojoules per hour were lost of energy across that steam times the efficiency, the would just be the rated efficiency of that turbine. So remember, this is our flow rate. Flow rate, dot meaning that it's a rate of our flow of a fluid, and we think back to sort of thermodynamics and fluid mechanics at this point. This is the change in enthalpy, not entropy, enthalpy times your efficiency. Our flow rate is 10,000 kilograms per hour. And we have gone from 2,800 to 2,600 kilojoules per kilogram. And we would multiply that by our efficiency, which is 0.95, which is a unitless measure. But again, we want kilojoules per hour, right? Because a kilowatt is a kilojoule per hour. If we remember here that a watt is a joule per second, and we can express we can change this energy and express it in any sort of our scientific notation that we want. And this is time in the bottom here. So I am looking for kilojoules per hour as my energy over time, which is work, right? Energy over time is work. Those are the units that I am looking for here. So I'm just going to change, what do I have here? Let's see. There is 1 kilowatt. Let me see. If I were to multiply that by 3,600 to convert from kilowatt hours to my kilojoules, then I would be able to have my kilojoules and my hours, and my hours And I would be left with, oh, here's my kilograms gone, my kilowatts. I would be left with my kilowatts. So, and if I were to solve that, I would get 527.8 kilowatts. And that would be 528 with our significant digits kilowatts of work that would go through this turbine. Let's look at what this turbine looks like. It has steam that enters the turbine and then exits the turbine with an enthalpy in and an enthalpy out. And we would look at that as, we would draw that as an insulated turbine with heat loss Q out equals 0. So just looking at the flow rate of the steam going in and the amount of enthalpy it lost, and the fact that it is a 95% efficient generator that this work is going into, then we would expect 528 kilowatts of energy. And that is a topping cycle, an example problem of a topping cycle and how much work would come out of just that turbine attached to a generator.